Today, we're going to learn about systems of equations. And the equations that we'll be talking about today are all going to be linear. So that means that they have a constant slope, they look like a straight line, and we can write them in slope-intercept form, which is y equals mx plus b, where the slope is m and the y-intercept is b. A system of equations is two or more equations that share the same variables. So we're really familiar with x and y, and these two equations both have an x and they both have a y. When we talk about the solution to a system of equations, we're talking about the values of x and y that make both equations true. So in other words, when you plug in something for x and you plug in something for y into both equations, it works. Today we're going to work on three methods of finding a solution, which are graphing, substitution, and elimination. But we want to pay more attention to graphing and substitution. Now we'll look at a real-life situation where using systems of equations can help us answer a question. Carlos has $28 and is saving $3 per day. Martha has $60 and is spending $5 per day. In how many days will they both have the same amount of money? Let's use orange to represent Carlos and blue for anything that has to do with Martha. So Carlos has $28. That's what he's starting with, so we know that's our y-intercept. That's the amount of money he has at 0 days. And he's saving money, so his money is increasing. And we have $3 per day. That tells us that this is a rate, so I know the $3 is the slope. Now Martha starts with $60, so that's her y-intercept. And she's spending, which means her money is decreasing, $5 per day. So that's our slope, -5. Now we'll use those slopes and y-intercepts to write our equations in y equals mx plus b form. So for Carlos, I have y equals 3x plus 28, where x is the number of days. And Martha's equation would be y equals -5x because she's spending money plus 60. Down below, I'll fill in my xy table based on the equation. The x represents the number of days and the y represents the money that Carlos has. So I'm going to start with $28 on day 0, and then every day I'm just going to add $3 because he's saving $3 per day. We'll do the same for Martha, starting at 60 because that's the amount of money that she's starting with on day 0. And then she's decreasing by $5 per day because she's spending $5 per day. Now I'm going to plot those points on the graph, both for Carlos and then for Martha. So the graphs of these lines represent how much money Carlos has per day and how much money Martha has each day. And on day 4, where these lines intersect, both people have $40. So I'm circling that intersection in purple. And this is what we can call the solution to our system of equations. You can see this in the tables to the left that we filled out as well, that they both contain the point 4, 40. So what this means in the context of our problem is that this is the point where Carlos and Martha both have the same amount of money. On day 4, Carlos and Martha will both have $40. So we just solved the problem by graphing, but now let's take a look at how to solve the problem using substitution. We're going to use the same two equations, but now we're going to look for variables that we can substitute for each other. When we want to substitute for our variables, we have to look for things that are equivalent, which means equal to each other. Once we find expressions that are equivalent to each other, we can substitute them or plug them in. With the way these equations are set up, I see that we have y equals something in Carlos's equation, and in Martha's equation, we also have y equals something. So y has to equal y, right? Y is the same letter, it's the same variable. So that means that the things on the other side of the equal signs also have to be equal to each other. So here I'm showing you y equals y, and I can replace this yellow y from Carlos's equation with the other side of the equal sign. If y equals 5, then 3x plus 28 also has to equal 5. And I'm going to do the same for Martha's equation. Instead of y, I'm going to replace that with negative 5x plus 60, which is equal to y. So these two equations were being set equal to each other. So now I have a new equation. 3x plus 28 equals negative 5x plus 60. And in this equation, I only have one type of variable, which is x, rather than y and x. So now we're going to solve for x like we normally would. I'm first going to try to get all of the x's on one side and all of the numbers without variables on the other side of the equal sign. Then I am going to continue to solve for x until I end up with x equals a number. So now we have x equals 4, but that's not our full solution yet. A full solution has an x part and a y part. So in order to find out what my y is when x equals 4, I need to plug x equals 4 back into one of the two equations that we started with. I'm just going to use the top one because that's easiest for me. After doing all that work, we find out that the y part of our solution is 40. So just like the solution that we found by graphing, our x equals 4 and our y equals 40. Let's go back to solving by graphing for a minute. So there's three types of solutions we can have with a system of linear equations. We can have one solution, and that's when we have intersecting lines, like in the example we just did. We can have no solution, which is where we have parallel lines. The lines will never intersect. And we can have infinite solutions. And it says coinciding lines right there. That means the lines lie directly on top of each other. They're the same line. So first, let's look at a system of equations that has one solution. I'm going to do everything with the top line in orange and the bottom line in blue. I'm first going to plot the y-intercept of the orange line, which is at 4, and I will go down 2 over 1 for every point after that. Now let's graph the blue line, starting at the y-intercept of negative 5, and I will go up 1 and over 1 for every point after that. Our point of intersection of these two lines happens at the point 3, negative 2, which is our solution to the system of equations. When I see that the equations of these two lines have different slopes, they have different m values, that is a big hint to me that this situation will only have one solution. Now let's see what happens when we have parallel lines. These lines, when we graph them, since they have the same slope, they will never intersect. So there will never be a point where we'll have a solution where the same x and y value works for both lines. That'll never happen. So a shortcut I know is that when two lines have the same slope but different y-intercept, I know that there is no solution. Now we come to this last situation, which is these coinciding lines. And right now they don't look like they have the same slope, so I'm just going to go ahead and graph both of these lines. When I graph both of these lines, I actually find out they're exactly the same. And when I look closer, I see that the slope of the second line is 2 over 4, which can be simplified to 1 over 2, which is the same as the slope of the first line. So my hint that a system will have infinite solutions is that the equations have the same slope and the same y-intercept. They're the same line. Now we're going to learn how to check if our solution that we found is actually the solution to the system of equations. So checking your solution isn't just checking your work to make sure you didn't make a mistake. It's actually something that you need to start practicing, because when you learn more difficult equations, there will be times where you get kind of false solutions, when you get fake solutions, and they don't work when you plug them back in. So this part is more important than just making sure you add it and subtract it correctly. So what we're going to do is for each equation, we're going to plug in x equals 3 and y equals negative 2 at the same time to make sure that this set of points works for each equation. When I plug in 3 for x and negative 2 for y, I'm no longer solving anything. I'm not moving things from one side to the other. I'm keeping everything on the side that it's on, and I'm keeping it there. I'm just simplifying both sides of the equation separately. What I want to happen when I've simplified both sides of the equation is that I get a true statement. So I get one thing equals the same thing on the other side. If here I got -2 equals -2, that's true. They're the same number, they equal each other. But if I got 3 equals -2, that's weird. 3 doesn't equal -2, at least not in this world. So then I would know that either there was a mistake on my part, or this is not a solution to the system of equations. I'm going to repeat the same process with the second equation to make sure that my solution works for that equation as well. And I got -2 equals -2 again, which is another true statement, so that I know that the point 3, -2 is a solution to my system of equations.